Hello everyone, welcome to our exploration of Class 10 Mathematics, specifically Chapter 1.1. You might be wondering why we start our journey here with these particular ideas about numbers. Well, this chapter lays a very important foundation. It's like building the ground floor of a tall skyscraper. If the ground floor is strong and well understood, everything we build on top of it will also be strong and stable. This chapter introduces some fundamental concepts about numbers, how they relate to each other, and a very clever method for solving certain types of problems. Think of it as getting to know the basic tools before you start a big, exciting project. These tools will be used again and again. Understanding the concepts in Chapter 1.1 is crucial not just for passing your exams, though that's important too. It's about developing your mathematical thinking. We're going to learn about how mathematicians long ago figured out ways to describe relationships between numbers. This kind of thinking helps you solve problems in many areas of life, not just in math class. It encourages logical reasoning and a step-by-step approach to finding solutions. So as we dive into this chapter, remember that you are building skills that go far beyond these specific topics. We are learning how to think precisely and systematically, which is a superpower in any field you choose to pursue later on. This first section, Chapter 1.1, often focuses on something called Euclid's division lemma and its application, Euclid's division algorithm. These might sound like complicated names, but the ideas behind them are actually quite intuitive once we break them down. We use division all the time without really thinking about the deep properties behind it. This chapter encourages us to look closer. It's about understanding the structure of numbers and how they behave when we perform operations like division. This deeper understanding will unlock new ways to solve problems, especially when it comes to finding things like the highest common factor of two numbers efficiently. So, get ready to explore some fascinating properties of numbers. We'll take it step by step, using simple language and plenty of examples. My goal is to help you see that these concepts are not scary, but actually quite elegant and useful. By the end of our discussion on Chapter 1.1, you'll have a solid grasp of these foundational ideas. You'll be able to use them confidently to solve problems. And hopefully you'll also appreciate a little bit more of the beauty and logic that mathematics holds. Let's begin this exciting journey together and make numbers our friends. Before we dive into the specific tools of Chapter 1.1, let's quickly remember what kind of numbers we are dealing with. In this chapter, and indeed in much of Class 10 mathematics, we are working primarily with real numbers. This is a very broad category of numbers. It includes all the numbers you are probably familiar with. Think about whole numbers like 0, 1, 2, 3, and so on. It also includes integers, which are positive whole numbers, negative whole numbers like -1, -2, -3, and 0. These are all part of the family of real numbers. We use them every day for counting, measuring, and many other tasks. But real numbers don't stop there. They also include rational numbers. Rational numbers are any numbers that can be expressed as a fraction p over q, where p and q are integers, and q is not 0. So, numbers like 1/2, 3/4, -2/5, and even whole numbers like 5, which can be written as 5 over 1, are all rational numbers. This category also includes terminating decimals like 0.5 or 0.75, and repeating decimals like 0.333, which is 1/3, or 0.142857, 142,857, which is 1/7. These are all numbers that can be precisely placed on the number line. Then there's another fascinating group within real numbers, irrational numbers. These are numbers that cannot be expressed as a simple fraction of two integers. Their decimal representations go on forever without repeating. Famous examples include pi, which you know from circles, and the square root of 2. These numbers might seem a bit mysterious, but they are just as real as integers or fractions, and they have their own important place on the number line. Together, rational numbers and irrational numbers make up the complete set of real numbers. This understanding forms the backdrop for the concepts we will explore. So, when we talk about applying Euclid's division lemma in Chapter 1.1, we are generally applying it to positive integers, which are a subset of real numbers. Knowing this broader context helps us understand where these specific tools fit into the larger world of mathematics. It's like knowing that a specific type of tree is part of a vast forest. The forest is the set of real numbers, and the tools we are about to learn help us navigate and understand certain parts of this forest, particularly the relationships between integers. This foundation will be very helpful as we move forward. Now, Let's get to the heart of Chapter 1.1 Euclid's division lemma. The word lemma might sound a bit formal. Think of a lemma as a proven statement that is used as a stepping stone to prove something else, or to perform a calculation. It's like a mini theorem that helps us with bigger tasks. Euclid was a very famous Greek mathematician, often called the father of geometry, but he also did important work with numbers. His division lemma is a very simple but powerful statement about what happens when you divide one positive integer by another positive integer. It's something you intuitively know from your earlier classes. Euclid's division lemma states that for any two positive integers, let's call them a and b, there exist unique whole numbers q and r such that a equals b times q plus r, where 0 is less than or equal to r and r is less than b. Let's break this down. Here, a is the dividend, the number being divided. B is the divisor, the number you are dividing by. Q is the quotient, the result of the division, how many times b fits fully into a. And r is the remainder, what's left over after b has fit into a as many times as possible. The crucial part is that the remainder r must be greater than or equal to 0, and strictly less than the divisor b. Let's take a simple example. Suppose we want to divide the number 17, our a, by the number 5, our b. We ask ourselves, how many times does 5 go into 17? It goes in 3 times, 5 times 3 equals 15. So our quotient q is 3. What's left over? We have 17 minus 15 equals 2, so our remainder r is 2. We can write this using Euclid's division lemma as 17 equals 5 times 3 plus 2. Notice here that the remainder 2 satisfies the condition, it is greater than or equal to 0, 2 is greater than or equal to 0, and it is less than the divisor 5, 2 is less than 5. This condition for the remainder is very important. The lemma also says that these numbers q, quotient, and r, remainder, are unique. This just means that for any given pair of positive integers a and b, there is only one possible value for the quotient q, and only one possible value for the remainder r that satisfy the conditions. You won't find another set of q and r that works. This uniqueness is what makes the lemma so reliable and useful for building other mathematical ideas, like the algorithm we'll discuss next. It's a fundamental truth about how division works with integers, and it's the bedrock of many number theory concepts. Let's try to visualize Euclid's division lemma to make it even clearer. Imagine you have a collection of A items, say 23 candies. You want to group these candies into boxes where each box B can hold, for example, 4 candies. The lemma helps us understand this process formally. So, A is 23 total candies and B is 4 candies per box. Now how many full boxes can you make? You can make 5 full boxes because 5 times 4 is 20 candies. This 5 is our quotient q. After filling 5 boxes, how many candies are left over? You'll have 23 minus 20 equals 3 candies remaining. This 3 is our remainder r. So, using the lemma's formula, a equals b times q plus r, we get 23 equals 4 times 5 plus 3. Let's check the condition for the remainder r. Our remainder is 3. Is 0 less than or equal to 3 and 3 less than 4? Yes, it is. 3 is greater than or equal to 0, and 3 is less than our divisor, 4. This simple example shows how the lemma perfectly describes this common situation of dividing and finding a remainder. The quotient q tells us how many complete groups we can make, and the remainder r tells us what's left over, which is always less than the size of one group. Consider another example. Let A be 30, and B be 6. If we divide 30 by 6, we find that 6 goes into 30 exactly 5 times. 6 times 5 equals 30. So our quotient q is 5. What is the remainder r in this case? Since 6 divides 30 perfectly, the remainder is 0. So we can write 30 equals 6 times 5 plus 0. Here, our remainder r is 0. Does this satisfy the condition 0 less than or equal to r less than b? Yes, because 0 is less than or equal to 0 and less than 6. This is perfectly valid. So the lemma works even when the division is exact and there's no leftover. The beauty of Euclid's division lemma is its universality for positive integers. No matter which two positive integers a and b you pick, as long as b is not 0, though the lemma is stated for positive b, you will always be able to find that unique quotient q and unique remainder r. This simple fact is incredibly powerful. It allows us to systematically break down numbers and analyze their relationships. This process of repeatedly finding quotients and remainders is the key idea behind Euclid's division algorithm, which we'll explore next to find the highest common factor of two numbers. Section 5, From Lemma to Algorithm, Euclid's Smart Trick for HCF. Now that we understand Euclid's division lemma, which is a equals bq plus r, let's see how it forms the basis of a very efficient method called Euclid's division algorithm. An algorithm is just a fancy word for a step-by-step procedure or a set of rules to be followed to solve a problem or perform a calculation. Euclid's division algorithm is a clever process that uses the lemma repeatedly to find the highest common factor, or HCF, of two positive integers. The HCF, also known as the greatest common divisor, or GCD, is the largest positive integer that divides both numbers without leaving a remainder. The core idea behind the algorithm is quite elegant. It relies on the fact that the HCF of two numbers a and b is the same as the HCF of b and the remainder r when a is divided by b. This might not be immediately obvious, but it's a crucial property. So if we have two numbers a and b, let's assume a is greater than b, we first apply Euclid's division lemma a equals bq plus r. If the remainder r is 0, then b is the HCF. Why? Because if r equals 0, then a equals bq, which means b divides a perfectly. Since b also divides itself, it must be the highest common factor. But what if the remainder r is not 0? This is where the algorithm continues. Since the HCF of a and b is the same as HCF of b and r, we now repeat the process with b and r. We take b as our new dividend and r as our new divisor. We apply the lemma again, b equals r times q, 1 plus 1 real, where 1 real is the new remainder. We continue this process with the previous remainder becoming the new divisor, and the previous divisor becoming the new dividend. Each new remainder will be smaller than the previous one. Remember, 0 is less than or equal to r, which is less than b. Eventually the remainder must become 0. When the remainder finally becomes 0 in one of the steps, the divisor at that stage is the HCF of the original two numbers, a and b. It's a systematic way of reducing the problem to smaller and smaller numbers until the HCF reveals itself. This algorithm is remarkably efficient, especially for large numbers, much faster than trying to list all factors of both numbers, and then finding the largest common one. It's a beautiful example of how a simple lemma can lead to a powerful computational tool, used even today in various forms in computer science and cryptography. Section 6, Step by Step, Finding HCF with Euclid's division algorithm. Let's walk through an example to see exactly how Euclid's division algorithm works in practice. Suppose we want to find the HCF of two numbers, say 455 and 42. We will use Euclid's division lemma repeatedly. Remember, the lemma is a equals bq plus r. We need to identify the larger number as a, our dividend, and the smaller number as b, our divisor. So here a equals 455 and b equals 42. Step 1. Apply Euclid's division lemma to a equals 455 and b equals 42. We divide 455 by 42. 455 equals 42 times q plus r. When you divide 455 by 42, 42 goes into 455 10 times. 42 times 10 equals 420. The remainder is 455 minus 420 equals 35, so q equals 10 and r equals 35. Our equation is 455 equals 42 times 10 plus 35. Since the remainder, 35, is not 0, we continue. Step 2. Now our new dividend a becomes the previous divisor, 42, and our new divisor b becomes the previous remainder, 35. So a equals 42 and b equals 35. Apply the lemma 42 equals 35 times q plus r. When you divide 42 by 35, 35 goes into 42 one time. 35 times 1 equals 35. The remainder is 42 minus 35 equals 7, so q equals 1 and r equals 7. Our equation is 42 equals 35 times 1 plus 7. The remainder, 7, is still not 0, so we continue. Step 3, again the new dividend a is the previous divisor, 35, and the new divisor b is the previous remainder, 7. So a equals 35 and b equals 7. Apply the lemma 35 equals 7 times q plus r. When you divide 35 by 7, 7 goes into 35 5 times. 7 times 5 equals 35. The remainder is 35 minus 35 equals 0. So q equals 5 and r equals 0. Our equation is 35 equals 7 times 5 plus 0. Aha! The remainder is now 0. The algorithm stops here. The divisor at this stage is our HCF. The divisor was 7, therefore the HCF of 455 and 42 is 7. This step-by-step process might seem a bit long at first, but it's very systematic. You just keep applying the lemma, making the old divisor the new dividend, and the old remainder the new divisor, until you hit a remainder of 0. The last non-zero remainder, which was the divisor in the final step, where the remainder became 0, is your HCF. Practice with a few more pairs of numbers, and you'll find this method becomes quite quick and easy to use. It's a really reliable way to find the HCF. Section 7. More HCF adventures, tackling different types of problems. Let's try another example of finding the HCF using Euclid's division algorithm, perhaps with slightly larger numbers, to build more confidence. Suppose we need to find the HCF of 12,576 and 4,052. Here, A, the larger number, is 12,576 and B, the smaller number, is 4,052. We will follow the same systematic application of Euclid's division lemma, which states A equals BQ plus R. Remember, we're looking for the step where the remainder R becomes 0. The divisor B at that step will be our HCF. Step 1. Apply the lemma to A equals 12,576 and B equals 4,052. 12,576 equals 4,052 times Q plus R. Dividing 12,576 by 4,052, we find that 4,052 goes into 12,576 3 times. 4,052 times 3 equals 12,156. The remainder is 12,576 minus 12,156 equals 420. So, our equation is 12,576 equals 4,052 times 3 plus 420. The remainder, 420, is not 0, so we proceed. Step 2. Our new dividend is 4,052, and our new divisor is 420. Apply the lemma, 4,052 equals 420 times Q plus R. Dividing 4,052 by 420, we find that 420 goes into 4,052 9 times. 420 times 9 equals 3,780. The remainder is 4,052 minus 3,780 equals 272. So, our equation is 4,052 equals 420 times 9 plus 272. The remainder, 272, is not 0, so we continue. Step 3. New dividend is 420, new divisor is 272. Apply the lemma, 420 equals 272 times Q plus R. 272 goes into 421 time, 272 times 1 equals 272. The remainder is 420 minus 272 equals 148. So, 420 equals 272 times 1 plus 148. Remainder, 148, is not 0. Step 4, new dividend is 272, new divisor is 148. 272 equals 148 times 1 plus 124. Remainder, 124, is not 0. Step 5, new dividend is 148, new divisor is 124. 148 equals 124 times 1 plus 24. Remainder, 24, is not 0. Step 6, new dividend is 124, new divisor is 24. 124 equals 24 times 5 plus 4. Remainder, 4, is not 0. Step 7, new dividend is 24, new divisor is 4. 24 equals 4 times 6 plus 0. Remainder is 0. Since the remainder is now 0, the divisor at this stage is the HCF. The divisor was 4. Therefore, the HCF of 12,576 and 4,052 is 4. This example involved more steps, but the process remained exactly the same. Each step methodically reduces the size of the numbers we are working with, guaranteeing that we will eventually reach a remainder of 0. This robustness is what makes Euclid's algorithm so powerful and widely applicable. It's not just about passing exams. It's about understanding a fundamental process in number theory. This skill is also foundational for understanding concepts in later mathematics, such as modular arithmetic, which has applications in computer science and cryptography. So, mastering this algorithm is a valuable step in your mathematical journey. Section 8, Euclid in the Real World, Surprising Uses of HCF. You might be thinking, this HCF stuff is interesting, but will I ever use it outside of math class? The answer is yes. The concept of the highest common factor, and by extension Euclid's algorithm to find it, has several practical, real-world applications, some of which are quite surprising. Understanding these applications can make learning about HCF much more engaging, as you see its relevance beyond textbook problems. It helps us solve problems involving sharing, dividing, or arranging things in the most efficient way. One common real-life scenario involves tiling. Imagine you have a rectangular room, and you want to tile the floor with square tiles of the largest possible size without cutting any tiles. How do you determine the side length of these largest possible square tiles? You would find the HCF of the length and the width of the room. For example, if your room is 455 centimeters long and 420 centimeters wide, you would find the HCF of 455 and 420. Using Euclid's algorithm, 455 equals 420 times 1 plus 35, 420 equals 35 times 12 plus 0, so HCF is 35. This means the largest square tile you can use would have sides of 35 centimeters. Another application is in arranging items or people. Suppose a school has two groups of students, one with 48 students and another with 60 students. They want to arrange these students into rows for an assembly such that each row has the same number of students, and that number is as large as possible, with students from each group not mixing in the same row, or mixing if the problem intends to find the largest group size possible for all students. If they want to find the largest number of students per row such that all rows are equal and only contain students from their original group, they'd find HCF of 48 and 60. HCF of 48 and 60 is 12. So they can arrange them in rows of 12. This ensures maximum equal rows. Furthermore, HCF is used in simplifying fractions. When you reduce a fraction like 24 over 36 to its simplest form, you are essentially dividing both the numerator and the denominator by their HCF. The HCF of 24 and 36 is 12. So 24 divided by 12 over 36 divided by 12 equals 2/3. In a more advanced context, concepts related to HCF and Euclid's algorithm are fundamental in cryptography, the science of secure communication. For instance, the RSA algorithm, widely used for secure data transmission, relies on properties of prime numbers and concepts related to finding HCFs and modular arithmetic. So, what you're learning now has connections to very modern technology. Section 9. You've got this. Mastering. Chapter 1.1 and moving forward. We've covered a lot of ground in exploring Chapter 1.1, focusing on Euclid's division, lemma and algorithm. We started by understanding why these concepts are important foundational blocks for your mathematical journey. We then revisited what real numbers are, setting the stage for the specific integers we work with in this chapter. The core of our discussion was understanding Euclid's division lemma, A equals BQ plus R, that simple yet profound statement about division and remainders. We saw it in action with everyday examples, making it more tangible and less abstract. Then, we built upon this lemma to learn about Euclid's division algorithm, a systematic step-by-step method to find the highest common factor, HCF, of two positive integers. We worked through detailed examples, like finding the HCF of 455 and 42, and then a more complex one with 12,576 and 4,052, showing how the algorithm consistently leads to the answer. The key is to remember that the HCF of two numbers is the same as the HCF of the smaller number and the remainder of their division. This insight is what powers the entire algorithm, making it efficient and reliable. To truly master these topics, practice is your best friend. Work through many different examples of finding the HCF using Euclid's algorithm. Try it with small numbers, then with larger numbers. You can even make up your own pairs of numbers and find their HCF. When you are performing the steps, clearly write down each application of A equals BQ plus R. Pay close attention to identifying the new dividend and new divisor at each stage. A helpful tip for remembering the lemma is to think of sharing items. A items shared among B groups gives Q items per group with R items left over, where R is always less than B. Don't be discouraged if it seems a bit challenging at first. Mathematics is often about understanding a process and then practicing it until it becomes second nature. Reread the explanations, watch videos if they help, like those on Khan Academy, and don't hesitate to ask your teacher or classmates if you have questions. The concepts in Chapter 1.1 are fundamental, and building a strong understanding here will make future chapters and more advanced mathematics much easier. You have the ability to master this. Keep practicing, stay curious, and enjoy the process of learning. Good luck!